We're going to look now at some applications of what we've been learning in statics class. And what I want you to pay attention to is that we are going to follow the same 4 steps in all of these applications. So it's the same process, just new applications. We're going to draw a free body diagram, perform force and moment balances, solve for geometry, and include force models, things like springs and friction and weight. A lot of times when you move into a new system, the only thing that changes is that we need some new force model. And I'll show you a couple more of those in this video. And then lastly, you solve for the unknowns. Same process, new applications. So this video is about pulleys and belts. The first thing we can look at here is a bit of a review. Pulleys are, or we can look at frictionless pulleys. And the force model, if you will, is that the tension in both strands are equal. That's a force model, so we can put that in this list. And so uh, a cable or a rope pulled over a pulley would have the same tension on both sides, even if they're at an angle to each other. The magnitude of the tension is the same, so you could break that into components. You'd get an X and a Y component. Those would add together to equal the tension. Even in really complicated situations like this multiple pulley system with a weight hanging from it, the tension everywhere through this system is the same. So if I were to say draw a free body diagram at joint 1, we would have the weight pulling down on the pulley, that's the tension there, and we would have the weight pulling out at an angle, that's the tension coming out that side, and so we would need some reaction force that looks equal and opposite to the sum of those two, which probably points up like that. If we came over here to joint 2, the tension is equal in both of these strands, again equal to the weight, and so we would need a reaction force that points down like this to hold that pulley in place. And lastly, if we came over to the flat wall at joint 3 here, again we just have W pointing through. Things get a little more interesting when we allow for friction. So now the big difference is the tensions are different. The most extreme case would be a belt in which there's no rolling whatsoever. It's just the cable or rope going straight over a round object. We're going to limit our attention to round objects. And so now we have T1 and T2, T1 and T2, and they are different from each other. And so we need a new force model to handle that if we're going to do anything with systems that involve belts. So it turns out the way the force model works is we're going to look at the angle at which the belt is in contact with the surface. That's a beta for the angle. And what we can think of is that we have a whole bunch of little segments of this circle, and as the belt goes around, each one has a normal force, and each one then has a little bit of a friction force going along the surface like so. And so you've got this little, say, mu times n1, and here it could be mu times n2, and so on all the way around. On this side, you'd get T2, and on this side, we get T1. If you were to do the sum of forces and work this out, you would discover that T2 is equal to T1 times the exponential e to the mu beta, where beta is that contact angle. And so what we have here is just a new force model. And so you could handle any system that involves a belt now by just using this substitution in the same kind of way that you would have used, say, the spring force or other friction forces, things like that. And of course, we could ask questions that go in lots of different directions. You could say, find the contact angle that allows this system to work, or all kinds of things like that. A fun example from my personal life is a rock climbing belay device, which is essentially just a couple of pins and the rope goes through it in a zigzag fashion, and then it runs up and over something. And so if you had a climber here, the climber is going to pull down on the rope with their weight, and I'm going to hold this end after having passed it through these devices and hope that that makes my life easier. If we look up the coefficient of friction in this case, it happens to be 0.4, And let's just assume that on each one of these little pins, the rope is in contact for exactly half the circle, or 180 degrees, so it's bent up and over. What we could do is we could call this T1, in between these two could be T2, in between these two could be T3, and then lastly over here we could have T4. And so as we work this out, we just use the equation we just saw, where T2 should be equal to T1 times the exponential of the coefficient of friction, which was 0.4, times the angle. Now, we need that angle in radians. I gave it to you in degrees, so we're going to have to multiply it by pi over 180 degrees to get it in radians. Remember, arguments of exponentials and trig functions need to be unitless. In other words, they need to be in radians. That tells us that T2 is equal to T1, in this case, times 3.51. Now, we do that again for the next pin, and we could similarly discover that T3 is equal to T2 times 3.51. And we could do it over the next pin, which tells us that T4 is equal to T3 times 3.51. But it's also equal to W. If you start adding these together and subbing things in, you discover that the weight is equal to T1 times 3.51 cubed. In other words, 43 T1. I get a 43 times reduction in the force. The tension that I have to pull on over at the other end, T1, is equal to weight divided by 43. And so just to give you some numbers, if this were, say, a 200-pound climber, divide that by 43, I only have to pull with 4.7 pounds, and that's why this device enables me to support my buddy when they fall, because of course I wouldn't. If I were climbing, I never fall. It's only them that do. Lastly, there are other uses for this. For example, if you've ever considered a belt, say in your car, the fan belt, something like that, the whole purpose of that belt is to make two different wheels spin. And so you've got a shaft here and a shaft coming out of this one. And what we can do is we can pull on these with a thing called a tensioning rod, I think it's called, until we get the tension we need in the belt so that the belt doesn't slip and it's able to transmit the torque of these two shafts. That would be another example of a place where you could use a belt. And even though it's on wheels that look like they're turning, the belt is not sliding relative to the wheels, and so it would in fact be a belt.